I'll get started. So first of all, your first homework assignment on chapter 19 is due on Friday. The next one on chapter 20 is due on the 4th. Um, we should finish up chapter 20 today, so that shouldn't be an issue. Uh, so we were talking about the electric potential and electric potential of point charges. So if you work out the difference in potential energy for a test charge, if you have a charge of plus Q at the origin, and you have a test charge at some point A, and you move it out to some point B along a radial line, we'll find the difference in potential energy between point A and point B is K Q naught Q over RA minus K Q naught Q over RB. You can get that by basically integrating against the force. From this, we can work out that to get a good difference in potential energy for any point, we can define our potential for a point charge. The electric potential of some point charge V is KQ over R, where we set our 0 point for electric potential to be at the distance of infinity. And so for a positive charge, you get a positive electric potential as you approach the positive charge. For a negative charge, you get a negative electric potential that increases as you approach the negative charge. And electric potential is 0 at infinity, and it gets bigger, or it grows as you get closer to other charges. If you have more than one charge, uh, the electric potential is fairly straightforward. We simply need to add the electric potentials from each individual charge. And the advantage here is that direction isn't important because it's a scalar quantity and not a vector quantity. So it's just the algebraic sum of each charge. Um, so yeah. Uh, so that's, the sum of the potentials for multiple charges. Uh, well, is just the sum of them. You can just add them together. So here's an example problem. We want to find the electric potential produced by a point charge of 7.22 times 10 to the minus 7 coulombs at a distance of 2.75 meters. Sure. So electric potential is KQ over R. So if we plug in our values, 8.99, K is 8.99 times 10 to the minus 9 Newton meters squared per coulomb squared. Um, our charge is 7.22 times 10 to the minus 7 coulombs. And the radius is 2.75 meters. So the voltage, the electric potential is 2,360 volts. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now here, it's sort of the other way around. We want to find the point charge that produces a potential of negative 5,120 volts at a distance of 3.55 meters. So here, voltage is KQ over R. We're trying to find Q. So Q is voltage times radius over K, which is going to be minus 5,120 volts times 3.55 meters divided by K, 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And this gives us a charge of negative 2.02 times 10 to the minus 6 coulombs, or negative 2.02 microcoulombs. And here, if we have a charge of 4.11 times 10 to the minus 9 coulombs, it's placed at the origin where x equals 0, and a second charge of minus 2q. So that will be negative 8.22 times 10 to the minus 9 coulombs is placed at 1 meter. What is the potential at 0.5 meters? And at what point between 0 and 1 is the potential? At some point between 0 and 1, the potential is 0. What is that point? Uh, so we'll start by finding the potential at 0.5 meters. That's fairly straightforward. The voltage for each individual charge is going to be KQ over R. We have two charges and two radii we have to figure out. So the total voltage is going to be KQ over radius 1 times K times minus 2Q over radius 2. Uh, if x equals 0.5 meters, radius 1 is going to be 0.5 meters, and radius 2 is going to be 1 meter minus 0.5 meters, which is also 0.5 meters. So we have 8.99 times 10 to the 9 Newton meters squared per coulomb squared times 4.11 times 10 to the minus 9 coulombs over 0.5 meters plus 8.99 times 10 to the 9 Newton meters squared per coulomb squared times negative 2 times 4.11 times 10 to the minus 9 coulombs over zero point 0.5 meters squared. So that's 73.9 volts minus 147.8 volts, which is 73.9 volts. Now, to find the point where the potential is 0, well, if you're at some point x in between 0 and 1 meter, radius 1 is going to be x, and radius 2 is going to be 1 minus x. So voltage is KQ over R. Total voltage is KQ over radius 1 plus K times minus 2Q over radius 2. Radius 1 is X. Radius 2 is 1 minus X. And the total voltage is equal to 0. So KQ over X plus K times minus 2Q over 1 minus X. We get KQ over X equals 2KQ over 1 minus X. You can cancel KQ from both sides. So 1 over X equals 2 over 1 minus X. Um, so 2x equals 1 minus x, so 1 equals 3x, x equals 0.33 meters. Uh, so it will be at the point at 0.33 meters. So a third of a meter from the first charge and 2/3 of a meter from the larger second charge. Any questions about that? Okay, I will continue. So here we have uh, two positive charges, one at -1 meters and one at +1 meters. And the question is, does the potential between these charges, does it look like a peak or a valley? So do you guys think this looks like a peak or a valley? You can answer in chat or you can unmute to answer. So I see peak, peak. Uh, it actually will look a little different than that. So you get something like a peak around each one. So the potential around each plus Q looks something like this. And then this around the other one. But their sum in the middle is going to be the sum of these. So you have peaks at each charge, but the sum, I'll put it in red, is going to look something like, it's going to be close to this. Oh, well, no, this would be lower. Uh, Let me see if I can draw this a little better. Drawing with my mouse on the screen is not the best, but it's going to be the sum. So you actually get a valley in between. Now I'm going to clear the drawings. Uh, yeah. Oh. So here we have three charges. So what's the electric potential due to the bottom charges at the top of the triangle? What is the initial electric potential energy of the top charge? And what is the kinetic energy of the top charge once it is moved infinitely far away? That's the questions here. And I need to move some stuff around here. So we have a charge of plus Q here. The distance is square root of 2d. We have a charge of plus 2Q. Distance is square root of 2d. And the charge up here is a plus 3Q. Because it's such. So electric potential is KQ over R. Well, K is just K. I'm going to leave, since this is entirely in variables, we can just keep K as K and Q is the appropriate Qs. And then the radius will be the radius for each individual one. So our total electric potential is going to be K times plus Q over the distance here, square root of 2d, plus K times 2Q from this one over square root of 2d. So that's kq over root 2d plus kq over 2kq over root 2d. So 3kq over root 2d. Our initial electric potential energy is just going to be voltage times charge. So U is going to be plus 3Q times V. So plus 3Q times 3KQ over 2D is 9KQ squared over 2D, square root of 2D. Sorry, not 2D, square root of 2D. Um, and then the kinetic energy, well, our potential energy plus our initial kinetic energy equals our final potential energy plus our final kinetic energy. Well, when it's infinitely far away, our potential energy goes to zero. So all our initial potential energy here has to convert to kinetic energy. So 9kq squared over square root of 2d equals 0 plus k final. So the final kinetic energy is 9kq squared over square root of 2d. Now, we can also draw, like on a contour map, curves of equipotential, constant potential. So on a contour map, the curves represent constant elevation, and the steepest slope is perpendicular to the curves. And the closer together the curves, the steeper the slope. Well, if we draw equipotential surfaces, electric potential and electric field have the same relationship. There are lines or three-dimensional surfaces of constant potential. The electric field is perpendicular to these equipotential surfaces and strongest where the surfaces are closest together. So this is an example with surfaces with equipotential lines spaced every half volt, up to a point, and then they just gave up. For one positive charge, so this is 1 volt, 1.5 volts, 2 volts, 2.5, 3, 3.5, 4. And there would be more lines, but they decided not to draw the infinitely many curves they would need. Here's a similar one for two positive charges. 1, 1.5, 2, 2.5, 3, 3.5, 4. And similarly over here. And here's one with equipotentials for a dipole, one positive and one negative. So uh, here we have, plus 4, plus 3.5, plus 3. Wait. 2.5, 3, 3.5. Okay. Well, here we have, these are the positive equipotential surfaces. This is 0. These are negative equipotential surfaces. They don't have values, so I can't say, but say this was 1, 2, 3, 4, 5, 6. This is 0, 1, 2, 3, 4, 5, 6 kind of thing. And you can see how the electric field lines are always perpendicular to the equipotential surfaces. So an ideal conductor will be an equipotential surface. So if two conductors are at the same potential, the one that's more curved will have a larger electric field around it. And this is also true for different parts of the same conductor. So ideal conductors will always be constant potential. And there are electric fields inside the human body. Our body is not a perfect conductor, so there are also potential differences. These are very important, actually. Many biological processes use potential differences created to send signals, do stuff. That's how you send nervous signals or trigger muscles and things. And an electrocardiograph is a device that plots the heart's electric activity. So you can look at how the heart is pumping by looking at the electrical signals you get at various parts on your body. Um, and you can see that the various, you know, parts, there's a cycle of your heartbeat, and the electric potential should follow a certain pattern. And if they don't, that's a sign that something's potentially wrong. And then they send you in for a more detailed test. Speaking from personal experience. You can also measure the electrical activity of the brain. This is an electroencephalograph. There are a lot more signals there because there's a lot more stuff going on rather than just your heartbeat, which also makes it a lot harder to interpret. So here's a question. Can equipotential surfaces intersect? Is that possible? So these are surfaces of constant electric potential. Could you have two of these surfaces intersecting? Feel free to answer in chat. Well, the correct answer is no, because if you had two surfaces intersecting, you would have two electric fields at the same point, because the electric field's always perpendicular to the surface. So you'd have two different electric fields at the same point, and that doesn't make sense. That's the wrong eraser. It is not possible. No. So here, these lines represent equipotential surfaces that are equally spaced in electric potential. So is the magnitude of the electric field near A greater than, less than, or equal to that near B? So remember, the electric field is proportional to the change in uh, electric potential. And each of these lines represents the same spacing in electric potential. So if this was, I don't know, let's say this was 0, this would be 1, 2, 0 volts. Um, 2, 3, 4, 5, 6, 7, 8. Just assuming that we have higher voltage on the left than the right. There's not really enough information. But do you think the electric field is bigger over near A or is it bigger over near C? I mean B. Blah. So because the electric potential is proportional uh, to the change, because the electric field is proportional to the change in electric potential, uh, the electric field near A is less than that near B because it's changing faster over here than over here. Bigger electric potential because of closer spaced line equipotential surfaces. Smaller electric potential because further spaced equipotential surfaces. So a capacitor is two conducting plates separated by a finite distance. Uh, so you have one equipotential surface on top, a different equipotential surface on the bottom. And the conductor will evenly spread the charge, and you'll get a constant electric field in between the two plates. That means you have equally spaced lines of equipotential between them. So there's a voltage difference between each side, an electric field between, and there is a concept for a capacitor. A capacitor is a thing here. We can relate the charge stored on each plate, because see here, this top plate has a charge of plus Q, this bottom plate has a charge of minus Q, to the electric potential between the two plates. Capacitors are sort of a very simple way to store charge. So to describe a capacitor, it has a capacitance, and the capacitance is the charge on each plate divided by the potential difference between the plates. And the unit is a coulomb per volt or a farad. So if you have a capacitor that's so many farads, a one so if you had a capacitor that was, say, 1 microfarad, that means if you had 1 coulomb of charge in that capacitor, you would have a potential difference of like 1,000,000 volts. And that's why actually a microfarad capacitor is a pretty big one. So here we have, okay, no, microfarad capacitor is not the same, but here we have a 0.55 microfarad capacitor charged to 12 volts. Let's figure out what the magnitude of the charge on each plate of the capacitor is. So here we have 12 volt. No, we have microfarad. Sorry, I was screwing up my math in my head. So don't worry about the numbers I was using when I was talking here. Let's do this correctly here. So here we have a capacitor whose capacitance is Q over V. So we have Q over V. And we want to find, we know the voltage. And the charge, the capacitance, and so we want to find the charge. So the charge is just going to be the capacitance times the voltage. So the more capacitance a capacitor it has, the more charge it can store for the same amount of voltage. So 0.55 times 10 to the minus 6 farads times 12 volts is 6.6 microcoulombs. Now here, let's say we have a capacitor that we find has a charge of 1.6 times 10 to the minus 6 coulombs when it's connected to a 9-volt battery. Well, capacitance is charge over voltage. So that will be 1.9 times 10 to the minus 6 coulombs over 9 volts, which will be 2.1 times 10 to the minus 7 farads, or 0.21 microfarads. Now, when we talk about capacitors, we can look at sort of an ideal capacitor, the simplest type of capacitor, a parallel plate capacitor. It's just two plates parallel to each other with a constant electric field in between them. So it's two plates of area A separated by distance D. And if we calculate the electric field you get using Gauss's law created by these charges, um, we'll find we can use that. The electric field is, you get an electric field of what is it? The electric field is going to be sigma, the charge density, over epsilon naught. Charge density is Q over area. So we can replace sigma is just going to be charge over area. So we get Q area epsilon naught, and voltage is going to be the magnitude of the voltage is going to be the electric field times the distance. There's some signs in here, but we don't really need to worry about that. Let me just. So this is going to be Q over area epsilon naught, and then capacitance is, of course, Q over voltage. So we have Q over Q over, oh no, there's a distance here. QD over area epsilon naught over QD area epsilon naught. The Q's cancel, and you get this formula. Epsilon naught area over distance. Any questions about that calculation before I clear it off the slides? Okay. So I'll just clear that. So the capacitance of a parallel plate capacitor, the simplest sort of capacitor, is epsilon naught area over distance. So we can use that to find relationships about capacitors, which we'll do in the next chapter. But so that's sort of the basic parallel plate capacitor. Now, the general properties of a parallel plate capacitor, the capacitance increases as the plates become larger and decreases as the separation increases. So to make a higher capacitance capacitor, you need bigger plates and smaller separation. Those both increase for any capacitor. That is true to all capacitors, no matter how they're designed. Lots of things have capacitance. In all likelihood, if you use your phone or some other thing, your phone probably uses measurement of capacitance to figure out where you're touching. Um, the modern capacitors that we actually use in electrical circuits are commonly coiled up as cylinders, uh, like a spiraling cylinders, because it's just easier. They take up less space. You could just take a big flat set of sheets and roll them up, kind of thing. So these are properties that are true to all capacitors. The more area you have, the higher the capacitance. The closer the plates are together, the higher the capacitance. Then there's some details, but those are some basic properties. So if you have a parallel plate capacitor and it has a plate area of 0.028 meters squared and a separation of 0.55 millimeters. Notice that that is in millimeters. If we want to find the charge on the plates of the capacitor with the potential difference between the plates is 20.1 volts and the magnitude of the electric field between the plates. Well, first of all, we need to find the capacitance. So to start, our capacitance is going to be epsilon naught plate area over plate separation. So epsilon naught is 8.85 times 10 to the minus 12 coulomb squared over Newton meters squared times 0.280 square meters. I'm sorry, 0.0280 square meters divided by 0.000550 meters, because that's 0.55 millimeters. So we need to convert that to meters to keep everything in the same units. So the capacitance is 4.51 times 10 to the minus 10 farads, or 0.451 nanofarads. That's a normal sort of capacitance. It's not a lot, but this isn't the best capacitor because the plates are, you know, but yeah, it's a reasonable sort of capacitor. Well, capacitance is charge over voltage. We want to find the charge. So charge is capacitance times voltage. So 4.51 times 10 to the minus 10 farads times 20.1 volts is 9.06 times 10 to the minus 9 coulombs, or 9.06 nanocoulombs. Reasonable amount of charge. And if we want to find the electric field, the electric field is going to be charge times epsilon naught over area, or it could be the voltage difference divided by the separation. So it's capacitance times voltage over epsilon naught area. So quick, epsilon naught area over distance, epsilon naught area. The electric field is voltage over distance. Not sure. Oh, this is from Gauss's law. Yeah. The electric field ends up being voltage over distance. So 20.1 volts, so divided by 0.0055 meters is 36,500 volts per meter. So capacitors are a way we can store charge. They're the simplest way to do that. So if I have a parallel plate capacitor that's connected to a battery that will maintain a constant voltage between the plates, if I move the plates apart, doubling the distance between them, what will happen to the charge on the plates? So remember, capacitance is epsilon naught area over distance. And So our initial capacitance will be epsilon naught area over distance, you know, epsilon naught times the area of the plates of the initial separation. Our second capacitance will be epsilon naught area over twice our initial separation. So capacitance 2 is going to be half of capacitance 1. But capacitance is charge over voltage. So charge is capacitance times voltage. So charge 1 will be capacitance 1 times voltage. Charge 2 will be capacitance 2 times voltage. But capacitance 2 is half of capacitance 1. So capacitance 2 is half of capacitance 1 times voltage. But capacitance 1 times voltage is charge 1. So capacitance 2 is half of capacitance 1. If I double the distance between the plates on a capacitor that's connected to a battery that keeps it at constant voltage, the charge on that capacitor will cut in half. Now, this is the simplest capacitor. It's just parallel plates with nothing in between. However, it's possible to improve capacitors by putting a dielectric in between the plates. So a dielectric is an insulator, but it's an insulator that can be slightly polarized in the direction of an electric field. Uh, so it's something that will act, that has charges in it that can move a little bit in an electric field and can become polarized. And this will do is that when you put a dielectric in between the plates of a capacitor, um, the charges will line up and oppose the electric field. Negative charges will be attracted slightly to the positive charges will be attracted slightly to the negative charges, and that'll effectively reduce the electric field. And that means for the same charge on the plates, you'll have less electric field, and because you have less electric field, you'll have less voltage, which means that for the same charge, you have less voltage. So if you add a dielectric to a capacitor, it effectively increases the capacitance, because the material in between polarizes and reduces the electric field, which reduces the potential difference across the plates, which means for the same charge you get less voltage, which means for the same voltage you can have more charge. Did that make sense? Now, what it does in purposes of a capacitor, um, the polarization of the dielectric results in a lower electric field within it. This new electric field is given by dividing the original field by this dielectric constant kappa. So electric field is your initial electric field divided by kappa. So the capacitance becomes kappa. The voltage becomes V naught over kappa. Q over V naught is capacitance. So it increases the capacitance by a factor of kappa. And pretty much all materials have some dielectric constant. Here are some examples. Water has a very high dielectric constant of 80.4. Neoprene rubber is 6.7. Pyrex glass is 5.6. Mica is 5.4. Paper is 3.7. Mylar is 3.1. Teflon's 2.1. Air is 1.00059. And vacuum is 1. Now, there are two factors you have to consider when choosing a dielectric for your capacitor. Ideally, you'd like as high a dielectric constant as possible, but there's another factor. Any dielectric has some limit of potential or voltage per meter, at which point it will stop being an insulator and start being a conductor. and that's the dielectric strength. So if the electric field in a dielectric becomes too large, it can tear electrons off the atoms, enabling the material to conduct, and this is called dielectric breakdown. And the field at which this happens is called the dielectric strength. And that's measured in the same units as electric field, which is in volts per meter. So the maximum electric field a dielectric can take in volts per meter, you want to try and maximize that, which is why, though water has a very high dielectric constant, seems like it would be great in your capacitor, its dielectric strength is very low. It's very easy to make water conduct. Uh, so it's a bad choice, actually. Uh, so mica is actually pretty commonly used in capacitors for a variety of reasons. It has a very high dielectric strength. It's 100 times 10 to the 6 volts per meter. Uh, so, but, and the other reason is that mica nicely turns into nice thin flat sheets that you can use. Teflon is about 60 times 10 to the 6 volts per meter. Paper is about 16 times 10 to the 6. Pyrex grass is 14 times 10 to the 6. Neoprene rubber is 12 times 10 to the 6. Air is 3 times 10 to the 6. But water is much lower, for example. So here's an example of a parallel plate capacitor with a dielectric. So a parallel plate capacitor with a dielectric, it has a plate area of 0.028 meters squared, a separation of 0.55 millimeters, same as the last parallel plate capacitor, but now we've added a dielectric with a dielectric constant kappa. When the capacitor is connected to a 12-volt battery, the plates have a charge magnitude of 3.26 times 10 to the minus 8 coulombs. So what is kappa? Well, the capacitance for a parallel plate capacitor with a dielectric ends up just being kappa times epsilon naught alpha over d. Basically, what you end up doing is you end up replacing epsilon naught with epsilon, which is the new permeability of that dielectric, which is just kappa times epsilon naught. But we're just going to use this kappa. So we want to find out what kappa is. Capacitance is charge over voltage. So kappa times epsilon naught area over separation equals charge over voltage. So kappa is going to be charge times separation over voltage times epsilon naught times area. And now we can plug all these numbers in. So 3.62 times 10 to the 8 coulombs times 0.55 times 10 to the minus 3 meters. That's the separation and the charge and the separation over the voltage, 12 volts times 8.85 times 10 to the minus 12 coulombs squared over Newton meters squared. It's epsilon naught times 0.0280 square meters. That's the area. Gives you a kappa of 6.7. So this dielectric increases the strength of capacitors by a factor of 6.7. So one of the things that the dielectric does is it effectively makes you can think about it that it kind of makes the separation smaller because it reduces the electric field. Now here we have a capacitor, two capacitors that are identical, except one of them has a solid piece of metal stuck in between the plates. Remember, the electric field inside a piece of metal is always zero. So, is the capacitance of A larger, smaller, or the same as the capacitance of B? What do you think the case is here? Is the capacitance of A here on the left bigger, smaller, or less than the capacitance of B here on the right. Remember, capacitance for a parallel plate capacitor under just normal circumstances is epsilon naught times area over separation. That's a D, not an S. Separation of the plates. And that's assuming you have some constant electric field here in between. Here you'll have some electric field here and some electric field here, but zero electric field in the middle. So is this going to have a bigger, smaller, or the same capacitance as the one on the left? So is A larger, smaller, or the same as B? Which one do you think is bigger? So you're saying A is smaller than B? That is correct. A has a smaller capacitance than B because basically that distance, this effectively has a distance of this long, but here on the second one for B, the distance only really applies to this portion. The middle bit where there's the piece of metal doesn't count. And so this effectively has plates that are closer together. So B has a higher capacitance than A. A has a smaller capacitance than B. I will clear my drawings and then, oops. Now, because capacitors store charge, they also manage to store electrical energy. So we can think about how much energy it takes to move an increment of charge from one plate to the other in a capacitor, and we can work out that the potential energy stored in a capacitor is the charge on the plates times the average voltage, which just ends up being half the charge times the voltage. And because capacitance is charge over voltage, you can write that as 1/2 capacitance times voltage squared, or charge squared over twice capacitance. Though 1/2 capacitance times voltage squared gets used more often because voltage is easy to measure and charge is hard to measure. That's just practicality. So we can figure out the energy stored in a capacitor. It is 1/2 the charge times the voltage, which is 1/2 the capacitance times the voltage squared. You can work this out by basically just integrating how much energy it would take to separate the charges in the capacitor. Um, because capacitance is charge over voltage, capacitance times voltage is charge over capacitance. That's how you can get these formulas from this formula. And the most useful of all of these formulas is probably this one, because voltage is easy to measure and charge is hard to measure. Now, the energy stored in a capacitor can be put into a number of uses. One of them that's pretty common is a camera flash. So a camera flash, like a traditional bulb camera flash, you want to dump a lot of energy into a light bulb very quickly. And one way to do it is that you charge up a capacitor slowly from a battery, and then you you output that energy very quickly outwards through the bulb of the capacitor. Defibrillators use large capacitors to allow for the big shock. You charge it up slowly and then you dump all that current out quickly from the defibrillator. And pretty much all electrical devices use capacitors in some way or another. They're all over the place. Um, but one of the things we can do is that a nice thing about a capacitor is that it has a constant electric field. So if we divide the stored energy in a capacitor by the volume of the capacitor, we find the energy per unit volume as a function of the electric field. And this energy density uh, for uh, is just the energy density of any electric field. It turns out to be consistent. So it's the electric energy per unit volume. It's 1/2 epsilon naught times the electric field squared is what it turns out to be. And this is extremely nice thing to know. Because now we know that it's the energy stored at any electric field. And it's possible to integrate over this for any sort of distribution of electric fields. So in a defibrillator, we have a 175 microfarad capacitor. 175 microfarads is actually pretty big. Most capacitors you run into on a daily basis are in the nanofarads. And it's charged to 2,240 volts. So what's the magnitude of the charge on the plates of the capacitor? And what is the energy stored in the capacitor? So magnitude of the charge, capacitance is charge over voltage. So charge is capacitance times voltage. So the charge will be 175 micro times 10 to the minus 6 farads times 2,240 volts, which gives you a charge of 0.392 coulombs. That's a lot of charge. Then we want to figure out how much energy is stored in that capacitor. Well, the energy stored is the charge times the average voltage, or 1/2 charge times voltage, or 1/2 capacitance times voltage squared, which is the one we're most likely to be able to measure. So 1/2 times 1.75 times 10 to the minus 6 farads times 2,240 volts quantity squared gives us 439 joules. And the advantage of a capacitor is that we can dump all that energy out very quickly and get a lot of current. So in a defibrillator, you're dumping that energy through your body, you're getting a lot of current, you're shocking your heart back into a functioning rhythm. You could also do it with 1/2 charge times voltage, so 1/2 0.329 coulombs times 2,240 volts, which is also 439 joules. So here we have some systems. We want to rank them in terms of the energy that is stored in them. And we want to calculate the individual energies. And we want to find the missing components. So here we have charge in coulombs, voltage in volts, and capacitance in microfarads. So let's go through these and work out how much energy is stored in each one and the missing components. So let's start with A. Our energy is going to be 1/2 capacitance times voltage squared. So 1/2 times 100 times 10 to the minus 6 farads times 5 volts squared is 1.25 times 10 to the minus 3 joules. And we want to find the missing charge. Charge is going to be capacitance times voltage. So 100 times 10 to the minus 6 farads times 5 volts is 5 times 10 to the minus 4 coulombs. B, energy is, we know, charge and capacitance. Well, here energy is charge squared over 2 coulombs. So energy is 1 coulomb squared over 2 times 200 times 10 to the minus 6 farads, which is 2,500 joules. 1 coulomb is a lot of charge. This is an even bigger capacitor, even more energy here. Well, this ends up with even more energy. Voltage is charge over capacitance. So 1 divided by 200 times 10 to the minus 6 farads. It's 5,000 volts. It's a much bigger voltage here. C, energy is 1/2. We know the charge and the voltage. Energy is 1/2 charge times voltage. So 0.3 times 20 times a half. So 1/2 times 0.3 times 20 volts. That's 30 joules. Capacitance is charge over voltage. Capacitance is 0.3 over 20 volts. That's 1.5 times 10 to the minus 2 farads, or 15,000 microfarads. This is the biggest capacitor. And lastly, D, energy is 1/2 capacitance times voltage squared. So 1/2 25 times 10 to the minus 6 farads times 10 volts quantity squared. So 1.5 times 10 to the minus 3 joules. So this has the exact same energy as A. And charge is going to be capacitance times voltage. So 25 times 10 to the minus 6 times 10 volts. It's 2.5 times 10 to the minus 4 coulombs. So largest energy is B. Then at 2,500 joules, C at 30 joules, and then A and D at 1.25 times 10 to the minus 3 joules. And so that's the end of chapter 20. So in summary, electric force is conservative and it has a potential energy associated with it. The change in electric potential energy, delta U, is minus the work. The change in electric potential, delta V, is the change in potential energy over the test charge. So the relation between electric field and electric potential is electric field is minus delta V over delta S. Or you can also write it for that the electric field is the gradient of the voltage. So this could also be written as, if you've done any multivariable calculus, you would write this to just deal with the extra dimensions. E is minus upside down delta V. But that's not actually important for this class, but this is sort of a way you can go from it's like a multivariable version of a derivative. The total energy is electric potential energy plus kinetic energy. That's conserved. Positive charges accelerate in the direction of decreasing potential. Negative charges accelerate in the direction of increasing potential. The electric field points towards the direction of increasing potential. The electric potential of a point charge. Oh, wait, no. Sorry, the electric field points in the direction of decreasing potential. It points from high voltage to low voltage. The electric potential of a point charge, V is KQ over R. Compare that to the electric field is KQ over R squared. Basically, because you took the derivative, because you took an integral of the no, yeah. To get the voltage, you take an integral of the electric field. Um, and so you go from radius squared to radius. The electric potential energy of 2 point charges, U is K Q naught over Q times R. And the total electric potential and total electric potential energies are sums due to these individual charges because they're not vectors, they're just scalars. Equipotential surfaces are those in which the electric potential is constant. The electric field is perpendicular to the equipotential surfaces. Ideal conductors are equipotential surfaces. And a capacitor is a device that stores electric charge. And capacitance is charge over voltage. And a parallel plate capacitor, which can have a dielectric with a dielectric constant in kappa, is kappa times epsilon naught A over D. A dielectric is an insulator that increases a capacitor's capacitance by a factor of its dielectric constant kappa, and a sufficiently large electric field can cause a dielectric to break down and become a conductor. Capacitor also stores electric energy. The energy stored is 1/2 QV, which is 1/2 capacitance times voltage squared, or charge squared over twice capacitance. And the energy density in electric field is 1/2 epsilon naught times the electric field squared. That's where we're going to stop for today. Having finished chapter 20. Any questions? If not, I'll see you guys on Wednesday at 2:30. Have a nice day. See you later this week on Wednesday.